November 12, 1942, Richmond, California. A complete cargo vessel, 441 feet long, weighing over 14,000 tons, stood ready to slide into San Francisco Bay. The ship had been assembled in just 4 days, 15 hours, and 29 minutes. In traditional shipyards across America, master builders had spent 6 to 8 months constructing vessels of similar size using techniques passed down since before the Revolution. Yet here, a complete Liberty ship stood ready for service, built by workers who had learned welding just weeks earlier. The crowd gathered at Permanente Metals Corporation Yard No. 2 included officials from the United States Maritime Commission, journalists from major newspapers, and competing shipyard owners who had traveled specifically to witness what they considered impossible. The mathematics of Allied victory were being written not in battle strategies, but in production statistics that would shatter every assumption maritime experts carried about shipbuilding limits. Standing among those watching was Vice Admiral Emory Land, chairman of the Maritime Commission. His expression revealed neither triumph nor celebration. He had authorized this construction attempt with deep skepticism, knowing that German U-boats were sending Allied shipping to the ocean floor faster than traditional yards could replace vessels. Britain was starving. America needed ships desperately. But Land also knew something the celebrating crowd did not yet understand. The revolution they were witnessing would soon reveal a fatal flaw that threatened to undermine everything. The transformation had begun nearly 2 years earlier, on December 27, 1940, when Henry J. Kaiser signed his first shipbuilding contract. A 58-year-old construction magnate who had never built a ship, never managed a shipyard, and had spent his career moving earth and pouring concrete for massive dam projects across the American West. Yet here stood a man who had just promised the Maritime Commission he would build 30 cargo vessels for the British government within 2 years. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Traditional shipbuilders dismissed Kaiser as a naive opportunist. The Todd Bath Iron Works, one of America's oldest shipyards, had reluctantly agreed to partner with Kaiser on the project, assuming their expertise would compensate for his ignorance. What none of them understood was that Kaiser's lack of shipbuilding experience would become both his greatest advantage and the source of a crisis that would force a complete reimagining of how ships could be built. The journey from skepticism to revolution began in early 1941, as Kaiser and his engineers examined traditional shipbuilding procedures. They recognized immediately that conventional methods would never meet wartime demands. Kaiser's chief engineer, Clay Bedford, had visited a Ford Motor Company assembly line in Detroit just weeks before. He had watched automobile chassis moving down production lines with workers installing prefabricated components at each station. He returned to California, convinced that ships could be built the same way. Traditional shipbuilders considered this comparison absurd. Ships were not automobiles. Maritime construction required precision craftsmanship developed over generations. But Kaiser saw opportunity where others saw impossibility. The first real shock came with his proposal to eliminate riveting entirely. Traditional ship construction relied on rivets, heated metal pins that were hammered through overlapping steel plates to join them together. A skilled riveting crew working with perfect coordination could install perhaps 100 rivets per day. Each Liberty ship required approximately 1 million rivets if built conventionally. The mathematics were devastating. At 100 rivets per day, a single crew would need over 27 years to complete one ship. Kaiser proposed using electric arc welding instead, a technique he had mastered building pipelines across the American West. Vice Admiral Land examined Kaiser's proposal with the weight of desperate necessity. His private correspondence, preserved in the National Archives, revealed the maritime establishment's reaction. Welding has never been proven reliable for hull construction at this scale, Land wrote. The British Navy forbids welding on warship hulls. Kaiser is proposing we bet America's supply lines on an unproven technology. Yet, Land also recognized desperation. In 1941 alone, approximately 3.6 million tons of Allied shipping would go to the ocean floor. At conventional construction speeds averaging 230 days per vessel, the Allies would lose the Battle of the Atlantic before American industry could respond. The decision to approve Kaiser's contract represented not confidence, but necessity. The Richmond shipyard rose from empty mudflats between January and December 1941. Kaiser's construction crews erected a facility that horrified traditional maritime engineers. Instead of the massive gantry cranes and longitudinal building ways that characterized established shipyards, Richmond featured something entirely different. The yard was laid out like an automobile assembly plant. Open areas for prefabrication surrounded 7 parallel building ways. Railroad tracks crisscrossed the facility, designed to move massive steel sections weighing up to 150 tons. Overhead cranes capable of lifting entire ship sections stood every 100 feet. John Riley, chief naval architect for Bethlehem Steel Corporation and a 30-year veteran of shipbuilding, visited Richmond in May 1941. His inspection report, marked confidential, contained both technical criticism and grudging admiration. Kaiser has violated every principle of efficient shipyard layout I learned in 3 decades of experience, Riley wrote. His prefabrication areas are too large. His crane capacity is absurdly excessive. His building ways are too short. Yet I must admit the facility is designed for exactly what he claims: rapid assembly of prefabricated sections. The arrival of workers provided the next phase of revolutionary change. Traditional shipyards recruited from established maritime communities where skills passed from father to son across generations. Kaiser advertised in newspapers across America, offering wages 20% above standard industrial rates and promising to train anyone willing to work. The first groups arrived in Richmond in August 1941. Among them were former secretaries, farmers, housewives, and labourers. Many had never seen a welding torch. Some had never held a job outside their homes. Kaiser's instructors didn't attempt to create traditional craftsmen. Instead, they taught specific techniques for specific tasks in approximately 2 weeks. Workers didn't need to know how to weld everything, only how to weld the vertical seams on bulkheads or horizontal deck plates or curved hull sections, which they would do repeatedly, thousands of times. The simplification of complex tasks into repeated simple operations, borrowed directly from assembly line manufacturing, proved devastatingly effective. By October 1941, Kaiser employed over 10,000 workers in Richmond, with fewer than 200 having any previous maritime experience. Traditional welders spent 4 years as apprentices learning comprehensive skills. Kaiser's workers were productive after 2 weeks of specialized training. As workers gained experience through late 1941 and early 1942, something unexpected occurred. The construction time for Liberty ships began falling dramatically. Kaiser's first Liberty ship took 197 days to build and deliver. Ship number 2 required 169 days. Ship number 5 required 128 days. Ship number 10 required 97 days. By spring 1942, Richmond was completing Liberty ships in 70 days on average. Traditional shipyards watched with growing alarm as this untrained workforce achieved production speeds that matched their own highly skilled crews. The prefabrication approach that traditional builders had dismissed proved its power. Instead of building ships from keel to deck in sequence, Kaiser's yards fabricated entire sections simultaneously across the facility. While one crew assembled a bow section in the prefabrication area, other crews built stern sections, deck houses, engine rooms, and bulkheads in parallel. When sections were complete, massive cranes lifted them onto the building ways where welding crews joined them together. Albert Wooding, production supervisor at Richmond Yard No. 2, explained the efficiency in a 1943 interview with Fortune magazine. In traditional shipbuilding, you cannot install the engine until the engine room is built. You cannot build the engine room until the hull is complete. Everything happens in sequence. Kaiser's approach allows parallel production. While one crew welds hull plates, Another crew assembles the engine in a separate area. When both are ready, we drop the completed engine into the completed engine room and weld it in place. Tasks that previously required weeks now take hours. The statistics of parallel production revealed manufacturing efficiency that seemed impossible to traditional builders. A conventional shipyard might have 50 workers attempting to install an engine over 3 weeks, working in the cramped confines of a partially complete engine room. Kaiser's prefabrication approach assigned 200 workers to assemble the complete engine and its mounting and structure in an open workshop over 5 days, then used cranes to position the entire assembly in a single 8-hour operation. More disturbing still to traditional maritime authorities was the casual elimination of centuries-old shipbuilding practices. Ships had always been built from carefully drafted plans that specified every detail. Kaiser used simplified drawings that provided basic dimensions and left details to workers' judgment. Traditional builders considered this recklessness. Kaiser called it flexibility. Vice Admiral Howard Vickery, Vice Chairman of the Maritime Commission and a career naval officer, initially fought against Kaiser's simplified specifications. His transformation from skeptic to supporter, documented in commission meeting minutes, illustrated the power of results over theory. In January 1942, I opposed Kaiser's request to reduce drawing specifications. Vickery wrote, "Ships are not automobiles. Maritime construction requires precision." But by March, Kaiser's yards were outproducing our traditional contractors by 40%. By June, the gap had widened to 70%. I learned that perfection is the enemy of sufficient. Kaiser's ships were not beautiful. They were adequate, and adequate ships delivered more cargo than perfect ships still under construction. As construction speeds increased through spring and summer 1942, competition developed among Kaiser's 7 shipyards spread across California, Oregon, and Washington. His son Edgar, who served as vice president and general manager overseeing the Pacific Northwest facilities, managed the Oregon Shipbuilding Corporation in Portland. Clay Bedford oversaw the Richmond yards in California. The two men, both driving and ambitious, began an informal contest to see whose facility could build ships faster. The race between Richmond and Portland became a public spectacle through fall 1942. Newspapers published updates like sports scores. Competition records fell repeatedly until Oregon Shipbuilding built the Joseph N. Teal in just 10 days in September 1942. Vice Admiral Vickery eventually ordered the speed competition stopped, declaring them stunt demonstrations that distracted from actual production goals. But the competition had served Kaiser's purpose. Workers across all 7 yards now believed that extraordinary speed was not merely possible, but expected. November 1942 brought the ultimate demonstration. Vice Admiral Land, visiting Richmond to inspect production, made an offhand comment to journalists that was overheard by Clay Bedford. The Admiral remarked that Liberty ship construction had improved remarkably, but noted that the recent speed record still paled compared to what mass production had achieved in other industries. Bedford took the comment as a challenge. He proposed to Vice Admiral Land that Richmond Yard No. 2 would attempt to build a complete Liberty ship from keel laying to launch in under 10 days, cutting the Joseph N. Teal's record in half. Land, skeptical but intrigued, authorized the attempt on condition it not disrupt regular production schedules. Bedford selected the 47th hull to be built at Yard No. 2 for the record attempt. The ship would be named SS Robert E. Peary after the Arctic explorer. Starting Sunday, November 8th, at 1 minute past midnight, over 1,000 workers operating in carefully coordinated shifts would attempt something unprecedented in maritime history. The prefabrication strategy reached its ultimate expression during the Peary construction. Every major component had been built, inspected, and staged before the keel touched the building way. The bow section, comprising more than 50 individual pieces, had been fully welded and equipped with anchor hardware, chain lockers, and forward crew quarters before assembly began. The stern section included the completed steering gear, propeller, shaft, and aft crew spaces. 4 complete cargo holds, each one a massive rectangular structure of steel, waited to be lifted into position. The engine, a 140-ton triple-expansion steam power plant built by Joshua Hendy Iron Works in Sunnyvale, had been mounted on its foundation structure and tested before leaving the factory. Where conventional shipyards built from keel to deck over months, Kaiser's yards assembled a nearly complete ship from prefabricated sections in days. 4 days into construction, the hull was complete. Engine installed, deck houses positioned, cargo holds secured, steering gear mounted. On Thursday, November 12th, at 3:30 p.m., just 4 days, 15 hours, and 29 minutes after the keel touched the building way, SS Robert E. Peary slid down the launching rails into San Francisco Bay. The crowd of observers included maritime officials, military officers, competing shipyard owners, and journalists from across America. Many arrived expecting to witness either failure or a compromised vessel that looked complete but lacked functionality. What they saw instead was a fully operational ship that required only minor fitting out before entering service. Vice Admiral Land, present for the launching, made brief remarks that were recorded by newsreel cameras. His words captured the maritime establishment's forced recognition that everything had changed. 6 months ago, I would have called this impossible, Land said. Traditional shipbuilding wisdom accumulated over 3,000 years said you cannot build a proper ship in 5 days. Henry Kaiser has made traditional wisdom obsolete. The psychological impact on traditional shipbuilders was profound and immediate. The same yards that had dismissed Kaiser as an ignorant outsider just 18 months earlier now sent engineers to study his approaches. The president of New York Shipbuilding Corporation, one of America's oldest and most prestigious yards, visited Richmond in December 1942. His confidential report to his board of directors revealed complete ideological collapse. Kaiser has achieved what our industry considered impossible by refusing to accept our limitations, the report stated. He treated shipbuilding as a manufacturing problem rather than a craft tradition. He simplified where we sought perfection. He standardized where we customized. He trained masses of unskilled workers where we cultivated generational expertise. The result is ships built in 1/10 the time, at 2/3 the cost. We must either adopt his approaches or accept irrelevance. By early 1943, Kaiser's influence had transformed American maritime production. 18 shipyards across the country were building Liberty ships using prefabrication and welding. Average construction time had fallen from 230 days initially to just 42 days by mid-1943. The United States was launching 3 Liberty ships daily, more tonnage than German submarines could sink. But perhaps the most devastating challenge to traditional maritime authority came from the quality of Kaiser's workforce. The tens of thousands of women, minorities, and untrained workers who had built these ships represented a direct repudiation of the old guild system that had dominated shipbuilding for centuries. At peak production in 1944, Kaiser's 7 yards employed approximately 196,000 workers. Of these, over 40,000 were women, representing a remarkable percentage of female industrial workers. By mid-1944, women comprised 27% of Richmond's production workforce. The 3 Northwest Kaiser yards alone employed over 31,000 women by 1944. African American workers numbered in the tens of thousands, employed in skilled positions including welding, fitting, crane operation, and even supervisory roles, a level of workplace integration unusual for 1940s America. The democratization of skilled work that Kaiser enabled carried implications far beyond wartime production. By proving that complex manufacturing could be performed by trained workers rather than requiring generational craft expertise, Kaiser's shipyards challenged fundamental assumptions about labor, skill, and industrial organization. By mid-1944, Kaiser's 7 shipyards had produced over 800 Liberty ships. The 18 American shipyards building Liberty ships had collectively produced 2,400 vessels. The scale of production was staggering. The United States was building merchant shipping at a rate that exceeded the combined capacity of the rest of the world. Commander Joseph Kenworthy of the Royal Navy, assigned to the British Admiralty delegation in Washington, watched American production with admiration and envy. His official reports, declassified in the 1980s, captured the British perspective. The United States is building merchant shipping at a rate that exceeds the combined capacity of the rest of the world, Kenworthy wrote. Kaiser alone produces more tonnage monthly than the entire British shipbuilding industry. The approaches are crude by Admiralty standards. The ships are inelegant, but they float. They carry cargo, and there are thousands of them. Then the ships started breaking, not from German torpedoes, not from storm damage. The ships were fracturing spontaneously, catastrophically, in conditions that should have been routine. On January 16, 1943, the SS Schenectady sat quietly at dock in Portland, Oregon. She was a brand new Liberty ship, barely 10 weeks old. No enemy action threatened her. No storm battered her hull. The morning was calm, the water still. Then, without warning, a sharp crack echoed across the harbour. Within moments, the entire vessel fractured completely in two, the hull splitting from deck to keel as if sliced by an invisible blade. Sailors scrambled as the bow and stern sections sagged in opposite directions, the ship's back broken while tied safely to the pier. The Schenectady wasn't alone. That same winter, the SS John P. Gaines broke apart in calm seas with the loss of 10 lives. The SS Esso Manhattan, a T-2 tanker built using identical methods, cracked so severely her crew abandoned ship in panic. Between 1943 and 1944, more than 1,000 Liberty ships reported serious structural failures, hull cracks, deck fractures, catastrophic splits. At least 19 vessels broke completely in half. 3 simply vanished at sea, disintegrating so rapidly they couldn't even send distress signals. These weren't war casualties. These were ships committing suicide. The maritime establishment's worst fears about Kaiser's revolutionary methods seemed vindicated. The welding had failed. The untrained workforce had produced defective vessels. The speed had compromised quality. Blame fell immediately on the shipyards, particularly on the women welders who traditional maritime men had never believed belonged in the industry anyway. Vice Admiral Land convened emergency investigations. Metallurgists examined failed sections under microscopes. Engineers reviewed stress calculations. Naval inspectors crawled through hulls with measuring instruments. Everyone searched for the culprit: bad steel, faulty welds, design flaws, inadequate quality control. Ships continued splitting while committees debated. Sailors grew terrified of their own vessels, knowing the hull beneath their feet might unzip without warning in cold Atlantic waters. Merchant mariners began refusing assignments to certain Liberty ships with known cracking histories. Some requested transfers or simply walked off. The miracle of mass production had become a maritime nightmare, and nobody could explain why ships built in record time were failing in record numbers. The conventional wisdom pointed to obvious culprits. The welders were inexperienced. The women and minorities who comprised much of the workforce lacked the skill and judgment of traditional craftsmen. The speed of construction had forced corners to be cut. Quality control had been sacrificed for quantity. The welds themselves must be defective. But inspection of the fractured ships revealed something puzzling. The welds looked solid. Metallurgical examination showed proper fusion, good penetration, acceptable quality. The steel itself met specifications, manufactured to the same standards used in riveted ships that had served reliably for decades. The designs came from proven British blueprints that had performed well in traditional riveted construction. Yet Liberty ships were fracturing like porcelain teacups. The cracks typically started at sharp corners, hatch openings, gun mounts, the squared-off design of the hull. Once a crack initiated, it propagated through the welded hull plates at terrifying speed, sometimes racing the entire length of a ship in seconds. Traditional riveted ships didn't suffer this problem, and the reason illuminated a fundamental difference that nobody had fully appreciated. Riveted construction is inherently discontinuous. Each riveted plate is a separate element. Cracks that start in one plate hit a riveted seam and stop. The overlapping plates and mechanical fasteners create natural crack arresters. Welded ships are continuous structures. A crack in one plate can run unimpeded through hundreds of feet of welded seams. The efficiency that made welded ships faster to build also made them vulnerable to failures riveted ships couldn't experience. The answer would not come from the shipyards. It would not come from the Maritime Commission's engineers or from the naval architects who had designed the ships. It would come from a British metallurgist working 3,000 miles away in Cambridge, England, who would discover that the problem wasn't the welding at all. Her name was Constance Tipper, and she was about to revolutionize the understanding of how materials fail. Constance Tipper was not supposed to be investigating Liberty ships. She was not supposed to be investigating anything related to wartime maritime disasters. In 1943, she was a lecturer in the Department of Engineering at Cambridge University, one of the first women to hold such a position at a time when most male lecturers had departed for wartime work. Her specialty was crystallography and the mechanical properties of metals, arcane academic work that seemed far removed from the urgent crises of warfare. But the British Admiralty Ship Welding Committee had a problem that conventional naval architects couldn't solve. British-built Empire ships, welded vessels similar to American Liberty ships, were experiencing the same catastrophic failures. The Admiralty needed answers, and traditional maritime expertise had failed to provide them. In desperation, they turned to Tipper, whose research on crystal deformation and metal strength had earned respect in academic circles, but had never been applied to practical shipbuilding problems. Tipper received sections of fractured hull plating from multiple failed ships. She examined them with the tools of fundamental materials science rather than the assumptions of maritime engineering. What she discovered would transform not just shipbuilding, but the entire field of structural engineering. The problem wasn't the welds. The problem was the steel itself, and more specifically, how steel behaves at different temperatures. Steel is not a single material with consistent properties. It's a complex crystalline structure that responds dynamically to temperature changes. At warm temperatures, steel is ductile. It bends, it flexes, it absorbs stress by deforming slightly. This ductility is what engineers relied upon. Materials tests conducted in laboratories at room temperature showed steel to be tough, capable of extensive plastic flow before failure. But Tipper discovered something that laboratory tests had missed. Below a critical temperature, steel undergoes a fundamental transformation. The material changes from ductile to brittle. The same steel that bent and flexed at room temperature would shatter like glass in cold water. The transition didn't happen gradually. There was a specific temperature threshold, different for each grade of steel, where the failure mode changed completely. The steel used in Liberty ships, a carbon steel designated as shipbuilding grade, performed adequately in warm water. But in the North Atlantic's near-freezing temperatures, below roughly 40 degrees Fahrenheit, the steel's ductility collapsed. It became brittle, losing the flexibility that normally allowed it to absorb stress. Cold steel didn't bend. It broke. Tipper developed a test to measure this phenomenon, a procedure that would become known as the Tipper test. She subjected small samples of steel to impact at various temperatures, measuring the energy required to fracture the material. The results were dramatic and unambiguous. Above the transition temperature, steel absorbed enormous energy before failing, the impact causing bending and deformation. Below the transition temperature, the same steel shattered with minimal energy absorption, fracturing cleanly with no plastic deformation. When Tipper tested samples from Liberty ship hulls, she found transition temperatures that ranged from -4 degrees Fahrenheit to 66 degrees Fahrenheit, averaging around 25 degrees. This meant that 90% of Liberty ship steel would exhibit brittle behavior at temperatures commonly encountered in the North Atlantic during winter convoys. But the brittle steel alone didn't explain the catastrophic nature of the failures. Tipper's investigation revealed a perfect storm of factors that combined to create disaster. The brittle steel provided the vulnerability. The welded construction provided the propagation path. But something else provided the trigger: stress concentration. The Liberty ship design, adapted from British blueprints, featured square corners at hatch openings. These sharp 90-degree angles created stress concentrations that multiplied local stress by factors of 3 to 4 times the nominal hull stress. In ductile steel, these stress concentrations would cause localized yielding, the material deforming slightly to redistribute the load. In brittle steel, stress concentrations became crack initiation points. When a Liberty ship hit cold North Atlantic water, the steel became brittle. Normal wave action and cargo loading created stress throughout the hull. At the square corner of a hatch opening, that stress concentrated. A microscopic crack initiated. In ductile steel, that crack would stop, absorbed by the material's ability to yield. In brittle steel under tension, the crack became a sprinting fracture. The physics were brutal and elegant. The crack accelerated, sometimes exceeding the speed of sound in steel, racing through the hull before bulkheads or frames could arrest it. The continuous welded structure provided no barriers, no riveted seams to slow the propagation. The SS Schenectady's fracture made perfect sense in hindsight. Built in early winter, her hull carried the locked-in stresses from welding. When Portland morning temperatures dropped to 28 degrees, the steel became brittle. The stress concentration at a hatch corner initiated a crack. That crack found a straight path through continuously welded deck plates and consumed the ship in seconds. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Tipper's findings reached the United States Maritime Commission in spring 1944. The implications were devastating and transformative in equal measure. Every Liberty ship built to that point carried the same vulnerabilities: brittle steel, stress concentrations at square corners, continuous welded structure with no crack arresters. Yet the solution wasn't to abandon welding and return to riveting. The solution was to fix the problems Tipper had identified. The Maritime Commission moved with remarkable speed once the true cause was understood. 3 parallel efforts began simultaneously. First, the steel specification changed. Metallurgists developed a new alloy with improved low-temperature toughness. The carbon content was reduced slightly. Manganese content increased. Small additions of nickel, expensive and rationed for armor plate, were justified by demonstrating that just 0.25% nickel content dramatically improved the steel's resistance to brittle fracture. The new steel, designated as killed steel because aluminum was added during production to remove oxygen, demonstrated dramatically improved toughness at low temperatures. Laboratory tests showed the transition temperature had dropped from approximately 40 degrees Fahrenheit in Liberty ship steel to near 5 degrees in the new alloy. This 35-degree improvement meant ships would retain their structural flexibility in conditions that turned Liberty hulls into fragile shells. Second, the design changed. Every square corner in the Liberty design was replaced with rounded transitions. The hatch openings that had birthed so many cracks were redesigned with generous radii. Engineering calculations showed that the sharp 90-degree corners in Liberty ships created stress multipliers of 3.5 to 4 times the nominal hull stress. The new rounded corners kept stress multipliers below 1.8. In practical terms, this meant a wave impact that would initiate a crack in a Liberty ship merely flexed a Victory ship's hull within normal elastic limits. Third, crack arresters were incorporated. Rather than continuous welds running hundreds of feet, the new ships incorporated riveted seams at strategic intervals. These hybrid connection points provided intentional discontinuities, places where a propagating crack would hit a mechanical joint and lose energy, potentially stopping before consuming the entire hull. The design accepted that cracks might initiate but engineered multiple arrest mechanisms to prevent catastrophic propagation. The new ship class, designated Victory ships, incorporated all of Tipper's insights, but there was another problem that needed solving: one that Tipper's investigation had touched upon but hadn't fully addressed. The welding itself, while not the primary cause of failure, contributed to the problem in ways that nobody had fully understood. The issue wasn't weld quality in the conventional sense. The welds were chemically sound, properly fused, adequately penetrated. But the act of welding itself introduced stresses into the structure that became locked in permanently. When a welder runs a torch along a seam, the localized temperature exceeds 2,500 degrees Fahrenheit. The metal expands dramatically in that heat zone. As the weld cools, it contracts. But the surrounding cold steel constrains that contraction. The result is residual tensile stress locked permanently into the structure. Traditional shipbuilders hadn't worried about residual stress, because riveted construction dispersed and relieved these stresses naturally through the mechanical assembly process. Welded construction accumulated and concentrated residual stress at specific points. When combined with brittle steel and stress concentrations, these residual stresses provided additional energy to drive crack propagation. The solution came from understanding how welding sequence affected stress distribution. If welders started at the edges of plates and worked inward, or began at one end of a long seam and ran straight to the other end, the cooling contraction pulled and warped the plates. Each completed weld locked that stress into the structure permanently. The stress accumulated and concentrated at the center of sections or at junction points. But if welders worked from the center of sections outward, allowing stress to dissipate toward the edges rather than concentrate in the middle, the residual stress distributed more evenly. If welding locations were alternated to prevent heat buildup in any single area, and if welds were completed in balanced sequences rather than long continuous runs, the locked-in stresses could be minimized dramatically. Kaiser's engineers, working with the insights from Tipper's research and their own practical experience, developed comprehensive welding procedures that specified exact sequences for every joint in the ship. The procedure manuals ran to hundreds of pages, detailing not just the sequence but the thermal management between welds. Welders learned to monitor interpass temperature, the heat level of the base metal between successive weld passes. If the steel exceeded 400 degrees, work stopped until it cooled naturally. This prevented the cumulative heat buildup that caused massive distortion in early Liberty ship construction, where welders sometimes worked continuously on long seams, superheating the steel into warped, stress-riddled configurations. The new procedures were tested exhaustively. When metallurgists examined hull sections constructed using conventional sequences versus the new methods, the difference was measurable and dramatic. Residual stress gauges showed traditional welds carried internal tensions exceeding 30,000 pounds per square inch, concentrated at key structural points. Sections built using the new sequenced approach distributed those stresses across broader areas with peak readings barely reaching 12,000 pounds per square inch. The steel was identical. The welds were chemically indistinguishable. Only the order of operations had changed, yet the structural integrity improved by factors that initially seemed impossible. In January 1944, Henry Kaiser made a decision that would either vindicate his industrial revolution or expose him as a reckless profiteer who had sent thousands of sailors to sea in defective ships. He ordered modifications to incorporate all the lessons learned from the Liberty ship failures. The gamble was staggering. Liberty ships were still desperately needed. The invasion of Europe, still months away, would require the largest amphibious logistics operation in human history. Every ship mattered, yet Kaiser was betting that he could implement the new welding procedures, redesign hulls to eliminate stress concentrations, upgrade the steel specifications, and somehow maintain production speeds that already seemed miraculous. His competitors thought he had lost his mind. Congressional investigators prepared to crucify him if production collapsed. The Victory ship program began in February 1944, with hulls that incorporated every lesson written in fractured Liberty ship plating. The rounded hatch corners replaced stress concentrators with smooth transitions. Deck and hull plate thicknesses were recalculated to ensure stress distribution matched the new welding sequences. Structural frames were repositioned to align with natural stress relief points rather than fighting against the welding pattern. The prefabrication system expanded dramatically. Rather than welding large sections on the ways where sequencing was difficult to control, Victory ships were broken into smaller modules constructed in dedicated shops. A bow section might contain 50 separate prefabricated assemblies, each welded in controlled conditions using optimal sequences, then stress-relieved in heating ovens before final assembly. The retraining effort was massive. Richmond shipyards employed over 90,000 workers by early 1944. Thousands were welders who had learned their trade in weeks-long crash courses. Now they needed to understand sequencing, stress relief, and thermal management. Kaiser established welding schools within the yards. Every welder received a numbered sequence card for each hull section. Weld number 1 here, number 2 there, never deviating from the prescribed order. The skeptics had ammunition when the first Victory ship keel was laid in February 1944. Construction took 18 days, slower than Liberty ship records. The second Victory ship took 16 days. Critics declared the program a failure, proof that quality and speed were incompatible. Kaiser ignored them. He was watching crack inspection reports, not just construction times. The first 2 Victory ships showed 0 stress cracks in post-construction inspection, not reduced cracks, 0. By April 1944, Richmond Yard No. 2 had transformed into precision choreography. The yard resembled an enormous assembly plant with distinct fabrication zones, feeding a central assembly area where hulls took shape with startling speed. The process began in prefabrication sheds, where welders worked on hull sections no larger than 30 feet in any dimension. Each section had a specific sequence card with numbered, color-coded welds. Welders started at position 1, always the geometric center of the section, and worked outward in a spiral or radial pattern. Supervisors walked the floor with checklists, ensuring nobody skipped ahead. After every 10 welds, sections went into stress relief ovens, heated to 1200 degrees and slowly cooled. This annealing process allowed the steel's crystalline structure to relax, dissipating residual stresses before they accumulated to dangerous levels. Assembly on the building ways followed a radically different sequence than Liberty construction. Instead of starting at the keel and building upward, Victory ships were assembled in large modules that came together almost simultaneously. The engine room section, the cargo hold sections, the bow and stern, all were constructed in parallel, then lifted by massive gantry cranes and positioned in a single coordinated operation. On June 27, 1944, the SS Benjamin Warner, Victory ship hull No. 23, was completed from keel laying to sea trials in 5 days and 11 hours. Not a stripped-down demonstration ship, but a fully equipped, combat-ready cargo vessel with defensive armaments, complete electrical systems, functioning engine room, and every weld executed to the new stress relief protocols. She carried no hull cracks. Her post-construction inspection revealed stress levels within normal operating ranges. When the Warner sailed for her shakedown cruise, she performed flawlessly in conditions that would have fractured early Liberty ships. The 5-day Victory ship wasn't just about speed. It represented a complete rethinking of how complex machines could be manufactured when engineering principles aligned with practical construction reality. Constance Tipper's discovery had cascaded into a systematic transformation of industrial shipbuilding. The proof emerged in operational service. Between June 1944 and the war's end in August 1945, 531 Victory ships entered service. Not one suffered catastrophic hull failure. Minor cracks appeared in a handful of vessels, stress concentrations that inspection caught before they propagated. These cracks were repaired using the same stress relief welding procedures, and the ships returned to service. The contrast with Liberty ships was absolute. The SS Wanda Fuka, a Victory ship, hit a mine off Okinawa in April 1945. The explosion tore a 20-foot gash in her hull below the waterline. Crew expected catastrophic crack propagation. Instead, the fracture stopped at the first riveted crack arrestor seam. She made port under her own power, was repaired in 6 days, and returned to service. A Liberty ship with identical damage, the SS Richard Hovey, suffered a comparable mine strike in February 1945, cracked longitudinally for over 90 feet, broke her keel, and sank in 14 minutes, with the loss of 37 crew. The human arithmetic of Victory ships versus Liberty ships played out across 2 oceans in 1944 and 1945, written in lives saved and missions completed that would have ended in disaster with earlier vessels. The Pacific Campaign's logistics would have been impossible without Victory ships' reliability. By June 1944, American forces were pushing across the Central Pacific toward the Philippines and ultimately Japan. Each island advance required millions of tons of supplies moved across thousands of miles of ocean. Liberty ships could make the voyage, but their structural fragility meant reduced cargo loads in rough seas, slower transit speeds to minimize hull stress, and the constant risk of catastrophic failure far from any rescue. Victory ships ran full loads at their design speed of 15 knots, 3 knots faster than Liberty ships, through typhoon-prone waters without the paralyzing fear that a cold night and rough seas would split the hull. By war's end, the total American maritime production between 1941 and 1945 exceeded 5,500 vessels, representing approximately 53 million tons of shipping. Kaiser's 7 shipyards had produced 1,490 ships, comprising 27% of total maritime commission construction. But the numbers told only part of the story. The revolution Kaiser initiated transformed global shipbuilding permanently. When Japan and South Korea rebuilt their maritime industries in the 1950s and 60s, they studied Kaiser's Liberty ship program and adopted his approaches as the foundation of their yards. The massive shipbuilding facilities in Ulsan, South Korea, and Nagasaki, Japan, that would dominate world shipping construction for decades were direct descendants of Richmond Shipyard's revolutionary practices. The prefabrication techniques, welding procedures, and parallel assembly approaches that Kaiser pioneered became standard practice in global shipbuilding. Every modern shipyard, whether building container vessels in Korea, oil tankers in Japan, or cruise ships in Europe, uses approaches derived from Kaiser's Liberty ship program combined with Tipper's understanding of material behavior. The technological innovations developed during the Liberty and Victory ship programs influenced industries far beyond maritime construction. The welding techniques refined under wartime pressure became standard in structural steel construction, petroleum refining equipment fabrication, and pressure vessel manufacturing. The stress relief procedures that prevented Victory ship failures became mandatory in bridge construction, pressure vessel codes, and offshore platform standards. Constance Tipper's discovery of the ductile to brittle transition fundamentally altered how engineers think about material selection and structural design. Before her work, engineers assumed that materials tested as ductile in laboratories would behave the same way in service. Tipper proved that temperature, stress concentration, and loading rate could transform ductile materials into brittle ones. Her insights became foundational to the new discipline of fracture mechanics. Modern nuclear pressure vessels, offshore oil platforms, Arctic pipelines, and high-rise buildings all incorporate design principles derived from understanding why Liberty ships failed and how Victory ships succeeded. The Tipper test, measuring the ductile to brittle transition temperature of materials, remains a standard specification for structural steels worldwide, 80 years after she developed it to explain why ships were splitting in the North Atlantic. The magnitude of Kaiser's achievement can be measured in statistics that reveal both the scale of the program and its remarkable success. 2,710 Liberty ships were built across 18 American yards between 1941 and 1945, an average of 1.8 ships per day at peak production. Kaiser's 7 yards alone produced 1,490 ships. Construction time fell from an average of 230 days for the first Liberty ships in 1941 to 42 days by 1943, with the record holder Robert E. Peary requiring just 4 days and 15 hours from keel laying to launch. Labor efficiency improved dramatically as workers gained experience and procedures were refined. The first Liberty ships required approximately 1.1 million worker hours to complete. By 1943, average worker hours had fallen to approximately 486,000 per ship. Kaiser's most efficient yards achieved construction in as few as 350,000 worker hours by utilizing 3-shift, 24-hour production schedules and maximizing prefabrication. Cost efficiency matched schedule improvements. The first Liberty ships cost approximately $1.75 to $2 million each. By 1943, costs had fallen to $1.8 million, despite rising wages and material prices, reflecting improved efficiency and learning curve effects. Victory ships, incorporating all the improvements and better steel, cost approximately $2.6 million, a 30% premium over Liberty ships. But the additional cost was recovered within months through eliminated failure risk and reduced insurance premiums. The battle casualty rates among Liberty ships demonstrated their effectiveness despite the structural problems. Of 2,710 Liberty ships built, approximately 200 were lost to enemy action, a loss rate of 7.4%. This compared favorably with pre-war merchant shipping loss rates. However, the structural failures told a different story. Approximately 1,400 Liberty ships, over 50% of the fleet, experienced some degree of cracking. Most cracks were minor, caught during inspection and repaired. But the 19 ships that broke completely in half represented catastrophic failures that killed crews and destroyed cargo. Victory ships, by contrast, suffered 0 catastrophic structural failures during the war. The difference wasn't just statistical, it was psychological. Crews on Victory ships operated with confidence. They pushed the vessels hard because the ships could take the punishment. That confidence translated to mission effectiveness, faster turnarounds in port, willingness to sail in marginal weather, aggressive maneuvering when under attack. Longevity statistics provided the ultimate vindication of both Kaiser's construction approaches and the improvements made based on Tipper's research. Liberty ships, designed as emergency vessels with expected service lives of 5 years, proved remarkably durable once crack-arresting modifications were retrofitted to surviving ships. Many remained in service for decades after the war. The SS John W. Brown, built in 1942, remains operational as a museum ship in Baltimore as of 2024, 82 years after construction. The SS Jeremiah O'Brien, also built in 1942, is preserved in San Francisco and participated in the 50th anniversary commemoration of D-Day in 1994, actually sailing to Normandy under its own power after 50 years of existence. Victory ships proved even more durable, with many serving commercially into the 1970s. The story of how Liberty ships broke and Victory ships succeeded ultimately stands as testament to a profound truth about engineering and innovation. The revolution wasn't just Kaiser's assembly line techniques or his willingness to train thousands of inexperienced workers. The revolution was the combination of bold industrial innovation with rigorous scientific understanding. Kaiser proved that traditional craft methods weren't the only way to build ships. He demonstrated that systematic processes and specialized training could produce results faster and cheaper than generational expertise. But Kaiser's initial success also revealed the dangers of innovation without complete understanding. The Liberty ships worked brilliantly until they didn't. The catastrophic failures exposed gaps in knowledge about how materials behave under real-world conditions. Constance Tipper provided the scientific foundation that Kaiser's industrial revolution needed. She explained why ships were breaking and what had to change. Her work transformed failure analysis from educated guessing into systematic science. The combination of Kaiser's manufacturing innovation and Tipper's materials science created Victory ships that were both fast to build and safe to operate. The lessons extend far beyond shipbuilding. Every complex system requires both innovative methods and deep understanding. Speed without knowledge produces spectacular failures. Knowledge without application remains academic curiosity. Progress requires both: the willingness to challenge conventional wisdom and the rigor to understand why conventional wisdom developed in the first place. Admiral Chester Nimitz, commander of the Pacific Fleet, reflected on the strategic impact of American maritime production in his post-war memoir published in 1960. "We fought across 5,000 miles of Pacific Ocean, supplied by ships built faster than the enemy could sink them," Nimitz wrote. Japan's military planners assumed American industrial capacity was impressive but finite. They believed that if they sank enough ships, eventually American logistics would collapse and we would be forced to negotiate. They failed to account for Henry Kaiser. By 1944, we were replacing shipping losses faster than they could inflict them. Industrial capacity, not martial valor, determined the outcome. The Pacific War was won in the shipyards of Richmond, Portland, and Baltimore, as much as on the beaches of Iwo Jima and Okinawa. In the end, Kaiser's greatest achievement was not the 1,490 ships his yards produced, but the transformation of what industry believed possible. The Robert E. Peary, built in less than 5 days, stood as tangible proof that tradition did not equal truth, that conventional wisdom could be questioned, and that revolutionary improvement required revolutionary approaches. But Kaiser's revolution alone would have produced thousands of ships that broke in cold water. Constance Tipper's contribution, less celebrated but equally crucial, provided the understanding that transformed rapid construction from reckless gamble into sustainable achievement. Together, they proved that industrial progress requires both courage and knowledge, both innovation and rigor, both the willingness to attempt the impossible and the wisdom to understand why previous attempts had failed. The Liberty ships are mostly gone now, scrapped decades ago or resting on ocean floors. The Victory ships that replaced them have largely followed. But the revolution they represented endures in every modern shipyard, in every welded structure designed to resist brittle fracture, in every materials test that measures ductile to brittle transition temperature, and in every engineer who questions whether impossible truly means impossible or simply means nobody has figured out how yet. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.